Hello physics class, it's Wednesday and here's your next video. We're going to be doing some sample problems for section 10.1, but first a message from Fernando Hernando. Okay, and then remember you can reach me here if you need to. After this video you will have to fill out a video response that says yes, you did watch this video, and yes, you did follow along and write down the sample problems as I did them in class. And so I hope that you have your pen or pencil ready. Also, do not attempt this without a calculator, so have your calculator ready to go. And I tried to do this on the board, but the glare was terrible. So I'm gonna do the little whiteboards because I can really zoom in and you can see it. You just really, trust me, could not see it well with me doing it on the board. So we're gonna start in your book on page 268. So this is gonna be page 268, and we're gonna do example problem 1 together. So turn in your book, and remember at any point, this is a video, so you can pause it so you can catch up and stay with me the whole time, because you need to be writing down these sample problems so that you'll have them tomorrow when you do problems yourself. So page 268, example problem 1, and that's going to be at the top in the green box. And so it says that you have a hockey player and he uses a stick to exert a constant 4.50 Newton force. So we're going to go ahead and write that down. We're going to say F is equal to 4.50 newtons. Write that down. Okay. Forward to a 105 gram puck. That's referring to the hockey puck. So that's mass, of course. So that's 105 grams, 105. You should see a red flag. You know what it is. It's the fact that the mass is only in grams and we need it to be in kilograms. So you can move the decimal place over 3 places to the left, or you can divide by 1,000. Okay, but that's going to be 0.105 kilograms. So make sure you make that adjustment. Very important. And then the problem goes on to say, how much work does the stick do on the puck? And of course, we're assuming that friction is negligible, our favorite thing. And so we're looking for work, which remember is a capital W. And remember, to save space, I'm not going to do the question mark. I'm just going to go right into the formula. Work equals force times distance. And, oh, you know what? I forgot. I did not write down the displacement. I've got to go back because I'm like, we're missing something. Okay, so here we go. We've got to do D is equal to 0.150 meters. So I left out that little tidbit. I was just so anxious to get to the equation. Okay, so of all of these things, there's like a factor that we don't need right now, and that actually is the mass. So sorry, we wasted a little time converting that. Okay, but we do have force, okay, which is the 4.50 newtons, and we do have distance, which I added back in, and so we just need to plug those in and solve. And so W is going to be equal to the force, which is 4.50 newtons, times the distance, which is 0.150 meters. Okay, so if you need to pause and do this in your calculator, you can do that, or maybe you're doing it while I'm talking. That's cool too. But by the time you round for 3 significant digits, it's 0.675 for your numerical answer. And then we need the unit. Okay, do you remember what work is measured in? It's joules, which would be a capital J. So make sure you put that, and I'm going to go ahead and circle that because that is our answer. So watch out for superfluous information, like the mass in this case, and then make sure you use the proper number of significant digits and all of the normal things. And so that's our first problem. And then for our second sample problem, we're going to stay on page 268. Okay, but we're going to skip down. We're not going to do problems 1 or 2. We're going to skip down to 3. And I don't know why my circle is so weird, but just go with it. So if you look at sample problem 3, now we're talking about a rock climber. It says a rock climber wears a 7.5 kilogram backpack while scaling a cliff. And so I'm going to go ahead and put mass is equal to 7.5. And then they were nice, they did kilograms. So we don't have to convert anything, yay. Okay, so we've got that going on. Okay, and it says that after 30 minutes, and so that's gonna be our delta T. And don't worry about it being in minutes for this period of time. After 30.0 minutes, we're just gonna write it down for now. Okay, the climber is 8.2 meters above the starting point. That's gonna be our D. So D is equal to 8.2 meters. And that is in the correct unit. We want our distances to be in meters. Good job. And then we have an A and a B. Okay, so A is how much work did the climber do on the backpack? So remember, work is equal to force times distance. And I know some of you are like, wait a second, we have distance clearly, but we don't have force. But remember, the force needed to move an object like up is equal to the weight, equal and opposite to the weight of the object, because gravity is pulling it down based on the amount of mass that it has, and we need to pull it up. If we're not accelerating it or anything like that, we can just pull it straight on up if we apply that same force, but in the opposite direction. So we're going to say, okay, that W equals, hang on. Oh, we're going to say that force, in this case, I'm going to put it off to the side, is equal to the weight. So I'm going to put this, I'll show you in just a second. This is a little challenging doing it like this. Okay, so the force in this case, when we have vertical things like going up and down, it's different from the first problem that we did because the hockey puck was on a horizontal plane. This is someone lifting a backpack up. And so that's going to be equal in value to the weight of the object. And I'm not worrying about positives and negatives right now. And then remember, weight is mass times acceleration due to gravity. And we're going to assume that this is taking place on Earth. So for this problem, our equation will be work is equal to mass times acceleration due to gravity times the distance it was moved up. Okay, and you can pause the video if you want and plug your stuff in, or you can just kind of plug in as I'm saying them, either way. Okay, so remember the mass of the object was 7.5 kilograms. Okay, and then acceleration due to gravity, we're going to do 9.8 meters per second squared, because we're saying that this is on Earth, of course. And then we're going to do the 8.2 meters. Okay, and so for A, okay, the work is going to be equal to, before you round, 602.7 joules. But how many significant digits can we have? Only 2. So this should round to 600 joules with a line over the 0. Bet you got that right. Good job. Okay, so let's move on to B. Okay, it says if the climber weighs 645 newtons. Okay, so now we're assuming the weight of, like we're doing like the climber and her backpack as one system at this point, because it's asking how much work does she do lifting herself and the backpack. Okay, so to do that, we just need to add in the weight of the backpack and the weight of the climber. And so I need to figure out, I've got to do the weight of the backpack, because I never actually did this like separately. So I've got to do the weight of the backpack. I'm just going to do it over here. So that was the 7.5 kilograms times 9.8 meters per second squared. Okay, so the weight of the backpack actually, where'd it go, is 73.5 newtons. Not going to worry about significant digits yet because it's not even my final answer. And so up here, I just did the weight of the backpack. And so the total weight, I'm just put F total, is going to be the 73.5 newtons coming from the backpack plus the weight of the climber. Wasn't that nice that they gave it in newtons so we didn't have to convert? I think so. So this is going to be plus 645 newtons. Okay, so that gives a grand total of 719 newtons, give or take. And I may have rounded that differently than you are, but that's okay. It's the concept of it. So when we do the total work, it's still going to be FD. So now we're going to use the 719 newtons, and they still went the 8.2 meters. So we're going to do 8.2 meters. Okay, and then we just need to multiply those two out. So use your calculator, multiply those together, and I got 5895.8 joules. So 5895.8 joules, but that is way too many significant digits. So when we round, we're only supposed to have 2, so it rounds to 5,900 joules. Nice. Okay, next problem. Okay, let's do on page 269. So right across the page, really. So page 269, we're going to do example problem 2. So just find that right across the page, and let's read that problem. It's about a sailboat. It says a sailor pulls a boat a distance of 30.0 meters. So that's going to be our D, 30.0 meters, along a dock using a rope that makes a 25.0 degree angle with the horizontal. So that's going to be our theta, 25.0 degrees. By the way, the other problems that we were working, this one as well as this one, occurred at 90-degree angles. So when I did my formula, it's really work equals FD cosine theta. But the cosine of theta is 1, so we just could not even consider that. We didn't have an angle to work with. It was implied that it was a straight-on force, so we were good to go with that. But if they give you an angle, you probably need to use the angle. Just a little tip there. So recorded the angle of 25.0 degrees. How much work does the rope do on the boat if its tension is 255 newtons? So that's going to be our force, our F. So 255 newtons. And then kind of check, is everything in the right unit? Like force is in newtons, distance is in meters. You've got your theta as a degree. Let me point out that I don't know what you're doing in math right now, but your calculator needs to be in degrees, not in radians. So take a moment, pause the video if you need to check it with the mode and make sure it's in degrees, not radians. And let's go ahead and work through this. And we're going to use the simple formula, work equals force times distance times cosine theta. And really, it's just a matter of plugging it in. And so work is equal to force, which is 255 newtons, times the distance, which is 30.0 meters, and then times our angle, well, the cosine of our angle, cosine of 25.0 degrees. Again, make sure your calculator is in degrees, not radians. Pause it if you need to. Okay, but you should come up with something like me, 6,933.25 joules. Too many significant digits, so we take that down to 3 significant digits. So that should round to 6,930 joules. Done. Okay, and then I think the last one that we're going to work, I know it's so weird doing it over video, so we're only going to do, I think, 4. But the last one we're going to do is going to be from page 272, problem number 10. So take a moment to find that. Okay, so 272, not the sample problem, not the example problem, but problem number 10. And so it says a 575 Newton box. And so that's going to be the weight. So remember, weight is F sub G. So I'm going to do 575 newtons to start off with. So we have a 575 Newton box. It's lifted straight up at a distance of 20.0 meters. And so D is going to be 20.0 meters straight up. A good unit for the distance there. By a cable attached to a motor. If the box moves with a constant velocity and the job is done in 10.0 seconds, so that's a time, that's going to be our delta T, 10.0, the seconds, that's the proper unit that we want for these time things because that goes with what's in a Newton. Okay, what power is developed by the motor in watts and kilowatts? And so automatically your answer is going to come out in watts because a watt is a joule per second. And then when we want to get the kilowatts, we'll just move the decimal place over 3 places to make it smaller or divide by 1,000. Both work the same way. Okay, so we need to remember the formula for power. And we're talking about, we're not talking about electrical energy here. So remember power, I'm just going to write it in because I don't want to lose out with the room that's on this little tiny dry erase board. But power equals change in work, well, work over change in time. So you may be thinking, oh my goodness, we don't even have work, but we do. We have what we need to get the work because remember, work equals FD cosine theta. That's the general equation. But since it's going straight up, I'm going to cross out this cosine theta. So work is equal to force times distance. And so I'm going to take that fact and plug it in down here. So I'm going to say that power is equal to F times D over delta T. Now when you write it like that, we do have everything we need. We have force, we have distance, and delta T. So let's start plugging stuff in. If you need more time than I'm giving you on this video, pause it, do it at your own pace, and then come back and check your answer. But we're going to do the 575 newtons, okay, times 20.0 meters. And then all of that gets divided by the 10.0 seconds. And remember that's going to be in watts automatically because a watt is a joule divided by a second. And when you set that up and you do it out, you should get 1150 watts. Okay, remember the W's can be confusing because when it's an answer for a problem, like after a number, the W stands for watts. When it's within a problem, like a formula, the W stands for work. Terribly unfortunate, so sorry, but that's the way it is. Okay, so that's in watts. And remember, I said if you want kilowatts, you can divide by 1,000 or just simply move the decimal place over to the left 3 places. Okay, so it's also equal to 1.15 kilowatts. I do not need that 0 on the end because I only needed 3 significant digits. And so you need both of those answers to satisfy this problem. Okay, and then that was the work for today. So your job was to listen to this video, which is almost 20 minutes long. Sorry about that. And then you just need to fill out the form that says, yes, you viewed the video, and yes, you followed along and wrote stuff down, and you turn that in. And then tomorrow for your work, you'll be actually answering some math problems based on all of this. So save your notes so you don't have to rewatch the video. And again, as always, okay, please contact me here if Fernando wants to send in some better things, because I think this is a little on the lame side. Sorry, Fernando, but you got to step up your game here. So I'll see you guys soon.